Okay, now let's talk about the acid-base experiment. First of all, in the end, we are going to build this. Looks like this graph, and the x-axis is the volume of sodium hydroxide you have used in the experiment, and the y-axis is the pH. And the pKa, we are looking for pKa. And what is pKa in this graph? It's the pH at half the equivalent point. So let's say the equivalent point is here. Let's say 7. Assume here equivalence is 10 mil. Let's just assume x equals 10 here. It's at the equivalent point. And then we look for x equals 5. We look for 5 because 5 is half of 10. And at this point, what's the y value? What's the y value for this x equals 5? And that pH is the pKa we are looking for. And for the first, we use two acids. The first acid, benzoic acid, is like it only has one proton. One molecule donates one proton. So you only have one pKa. The second acid has two protons. Each molecule can donate two protons. So it has two pKa's. The first pKa is it's like what we just covered. The second pKa is it's at the middle point of the first equivalent and the second equivalent. It's at here. And then you find the x, what the x is, and you go to this graph, this curve, and you find the corresponding y. And that y value is the pH. It's the pH and it's also the pKa2, the second pKa. And why is like this? So we have a weak acid here. This one is the Henderson equation. So when weak acid dissolves, it dissociates, and it gives this conjugate base. So 1-to-1 ratio. And if let's assume we have 10 of this molecule, HA molecule acid, and if half dissolve, if half of these 10 molecules dissociate, we get 5 of this conjugate base. Because we have 5, because at first we have 10, 5 dissociate, so which means 5 left. 5 of this molecule left. But since it's a 1-to-1 ratio, the 5 molecules, after they dissociate, they generate 5 of this conjugate base. So it's 5, 5. It's a 1-to-1 ratio here. It's 1-to-1. And it's 1-to-1 in this equation. If this part is 1, log 1 equals 0. This is mathematics. This is not chemistry. Because 10 to the 0 power equals 1. So log 1 equals 0. So this whole part will become 0. And if this part is 0, pH equals pKa. So it's at this equals this. That's half. When half of this HA converts to this conjugate base, then 50% of HA left, and then 50% of HA converted to this conjugate base. That's 1-to-1 ratio. Okay, that's the reasoning behind this. Now let's take a look at so after we got the pKa, how do we get Ka? So remember, P means negative log. pH actually means the negative log of the concentration of proton. That's what the pH actually means. You can actually calculate. If we know the concentration of proton H, we can actually calculate the pH based on this equation. So so what's pKa? It's very it's the same as pH. It's negative log Ka. And then if you know this relation, you can calculate Ka. I have given you enough hint. This should be easy to get the Ka. And the Gibbs free energy, the equation here, you can put Ka, you can plug in the Ka value from all these steps. You get a Ka, and you plug it in. You calculated the free energy, Gibbs free energy. And next, I suggest when you do your experiment, you use a computer to create an Excel sheet, and then you put the data in there. How many ml of sodium hydroxide, the base sodium hydroxide is added, and what the corresponding pH is. And in this picture, we remember we use a beaker because it has a larger opening. It's easier for you to do the measurement. This is a pH meter, and this is the burette. This is how you add the sodium hydroxide. So use a beaker, and it's easier this way for you to monitor the pH. All right. Good luck, everybody. I will see you guys in class.